This week, talking about kernel configurations. So we, a couple weeks back, we talked about how to run a basic kernel, just your first GPU function. And it has this form that you can see on screen. It's got this triple bracket notation and then your function parameters. So you've got vecadd as the name of the kernel we want to run. These triple brackets. This one says we want to run a single kernel block. Whoops. A single kernel block. And the 8 says we want that block to have 8 threads in it. So we're running a total of 8 threads. If you wanted to compare it to MPI, this would be the same as saying we're running 8 processes. Now, MPI processes and threads are different in quite a few ways, but that's just one way to think about it if you're not used to thinking in threads. So that's how we've kind of looked at launching a thread. And when we do that, we get this kind of, we can think about it using this image below. So we have 8 processes going, and we can use this inbuilt value. It's a value that's built into CUDA called thread IDX, which stands for thread index. We can use that to get each thread's rank. In this case, we're going to use the X dimension of that thread index, and there can be more dimensions, which we're going to discuss in a moment. We use the X dimension of that thread index, and that gives us a value that we can then use to determine the thread's rank. Again, going back to the kind of MPI analog, the rank can be used to make that thread do certain things or not do certain things. So a lot of times it's important to get a unique value for every thread. So in this simple case, where we launched one block of 8 threads, we can use thread index.x, thread idx.x, to get that value, because these are unique in themselves. So, any questions about what thread index is, or what I've done with this kernel launch code on this page?
Riley?
Mm-hmm.
I don't know whether this is out of context, but I thought threads have to be in a process within.
Well, go ahead, finish asking.
Like that threads are contained, can be contained within a process. But here it looks like threads are processes.
Yes, and that's kind of one of the problems with mixing analogies like I am. So in reality, a kernel should be treated like a single process. Well, in a way. So you launch this kernel, and from the perspective of the CPU, where you're launching all this from, that's treated as one thing that it tells the GPU to go do. Right?
Okay, I see.
But within that kernel, you can have those threads do different things.
Got you.
So, for example, if I wanted to fill an array, right? And I think we went over this example in one of the earlier classes. You can have a kernel that takes however many threads, and then you have that thread use its rank and say, I want to fill the array at my rank with a value. And that way each rank gets a different value. Each element in the array gets a different value based on the thread rank. So you're launching one process, but then each thread has a slightly different task inside that process.
I get you. Thank you.
Mm-hmm.
I agree.
Good deal.
Thank you.
All right. So this was the simplest form that we can launch a kernel, right? It's simple because we can identify a thread by one value. There's no computation. There's none of that. It just simply says, okay, you want to know which rank I am? I'm thread index.x. That's who I am. We're about to make that slightly more complicated by using multiple blocks. So first, let's look at the code for this. It's all the same, except for now we have a 2 here. This means we're launching 2 blocks of 4 threads. Now, the easiest way to think about that is just to say, well, we're launching 2 times 4, that's 8 threads. And that is an okay way to think about it for a lot of things. If we go back to that array example, that's perfectly fine. You're launching 8 threads. There's no impact on that whatsoever. When you get into slightly more complex topics, having things in separate blocks means separate memories. So there's some complicating factors there. But for our purposes today, it just means we have, in our case, the same amount of threads as before. We've just divided them into 2 groups, and those groups are called blocks. So because of that, if we want to kind of go back to our idea of finding a thread's rank, determining who it is out of all of the threads, we can't rely on thread index anymore. Because thread index, as you can see in this image here, thread index now repeats, right? It only identifies a thread within a block. So block 0 here has 4 threads. So we get thread indexes 0 through 3. It identifies each thread within the block that it's in. But then the thread index repeats again in block 1. 0, 1, 2, 3 again for block 1. So, okay, that's not going to work anymore. In addition to that, we're working with some new variables now that are introduced when we start using multiple blocks and multiple dimensions. But anyway, these are present all the time. It's not like they actually get added in when you change the way you launch a kernel. But now they actually have meaning for us because we need them to do things and they have meaningful values. So start off with what we know. Thread index is the index of something within the block that it's part of. Block index, block IDX, says this is the block number within the overall kernel layout. And the word for that is called the grid. That just means this is the collection of blocks that this kernel is running all at once. And then each block has its threads inside it. So anyway, that's the grid. And that's where grid dim comes from. So in this example, where we've got 2 blocks, then the grid dim in the x dimension is 2. And that's what we get by looking at grid dim.x. Same thing with block dimension. That's just the number of threads inside a block in a particular direction. So the block dimension here is 4 in the x direction. Another thing to point out here is that it's all in terms of x, like we add this dot x onto all of these. And that's because x is the default first dimension. You can use higher dimensionality and you'll use different axes for that, x, y, and z. But when you only use one dimension, it's always going to be x. So that's why I always have x on the input. So now that we've kind of talked about what all these different new variables are, let's actually use them and figure out how to get that unique rank value to use again. And you'll see here, kind of in the code at the bottom, I've already put the equation for you. So the way we can find something's rank is first, basically in all these examples, and it'll get more complex as we go, but basically all we're doing is summing the number of threads that comes before the one we want to determine the rank of. So in other words, if we wanted to find this global ID 7 without knowing that it's 7 prior, obviously, we have to know how many threads are in front of it to know that this one's going to be 7. So how do we add them up efficiently? Well, we can look at the block that we're in, because we know if we're in block 1, block 2, block whatever, there are that many full blocks before the block that we are in, the thread that we're interested in, is at. So in this case, we're looking at number 7 here. It's in block 1. So we know automatically we can include a full block's worth of threads and count that. So that's where this 1 times 4 comes from. We're in block 1. We know that there's a full block behind us. That's using blocked_in.4. So that's where that part comes from. Number of blocks times the block we are in, or number of threads per block times the block we're in. The last part for this setup is just to include the threads that are in the same block. Well, that's what thread index is. It tells you how many threads ahead you are from the beginning of this block to your position. And so that's 3 for global ID of 7. There's 3 threads in front of it, so we add 3. And so that's how you get this value of 7 for global ID 7, block ID, block index of 1, and thread index of 3. Does everyone see how I got there?
How do you get that 3? The one you add, the thread ID dot x.
I can't quite hear you, Grace.
The thread, the last one, is it for each of the threads in the block? The one in,
Yes.
okay.
Yeah, so I'll reiterate that, and I think it'll answer your question. So thread index is only concerned at the block level with distinguishing each thread. So if I've got 4 blocks in a thread, the only options I can have are 4 threads in a block, rather. The only options I can have are thread 0, thread 1, thread 2, and thread 3. If I would have another one, I'm going to jump into another block, and so it's going to start over again at 0.
Okay.
So another way to think about it is that thread index is just the offset of that thread within the block. If that makes any more sense.
Yeah, it does. I see.
All right, so did that answer it? I still can't quite hear you.
Yes, you answered it. Thank you.
Okay, good deal. Okay, now let's make it more complicated. I don't do this arbitrarily. It is because you could actually need a 2D kernel. So we looked at 1D kernels in one block, which is just using the thread index, right? Because thread index is the offset within a single block. So if you only have a single block, then that offset is the ID of each thread. And then we looked at one dimension with multiple blocks. And so you have to use the block number in each dimension and then the thread number within each block. Here, we're going to start working with 2 axes, X and Y. And for simple kernels, you probably won't need this. Because really what we're used to working with, at least so far in the class, is arrays or vectors. And those are all one-dimensional. So a one-dimensional kernel makes good sense for that. You wouldn't want to use a 2D kernel for those because it's really not a good fit. However, there are lots of applications that naturally will fit in a 2D grid. And in those cases, it makes a lot more sense to use the inherent nature of them being 2D in your kernel configuration, rather than trying to sort of flatten your problem to use a one-dimensional kernel. So that's kind of the motivation for why we want to do this. It will very often occur that we naturally fit that kind of picture for our thread layout better, as opposed to one-dimensional. So to create that kind of configuration, you can see down at the bottom here, there's this type called dim3. Dim3 is a built-in object type in CUDA. You don't have to import anything special or do anything like that. It's just part of CUDA. And you can see we create a new dim3 variable. It's going to be of length 4 in the x dimension and of length 2 in the y dimension. And later on, we'll use the same constructor with 3 variables to get a 3-dimensional kernel layout. So I've made this dim3. It says we want a layout that is 4 by 2, 4 in the x direction, 2 in the y direction. And then I just plug that, this dim3 value, into the vector addition kernel configuration. So now this tells me that I want one block, 1 dimension, that has a 2-dimensional thread layout, which is 4 in the x direction, 2 in the y direction. So let's look at that and kind of figure out what we're looking at here. This is kind of a visual layout of what this looks like. And I've set all of the values here, that way you can see what you would get from this. So the block dimensions come directly from our kernel. Block dim.x is 4, block dim.y is 2. And then we have our thread indexes. Now that we've used a 2D kernel, our thread index has 2 dimensions. And that is, of course, the x and y. We still have 8 threads, just like we did in the last example. Now they're laid out in this rectangle rather than just being in a line in 1 dimension. And that's going to change how we identify them later on as well. I think there's something else I was going to say here, but I've forgotten what it was. So we'll move on and maybe it'll come back to me. So determining rank. It's not as simple as just the thread index anymore, but it's close because we don't have multiple blocks to do. The only thing we have to do here is take that same idea from when we used multiple blocks in 1 dimension. All we want to do is just sum the number of threads or count the number of threads that came before the one we're interested in. So we'll look at ID 7 again. We don't know it's ID 7 yet. We got to figure that out based on the other information that is available to us, which is thread index and block dimensions. And there's also block index, of course, but that's always going to be 0 because there's only 1 block. So that doesn't actually help us. But here we've got the 4 values that do help us, the block dimension and the thread index. So if we're going to count the threads that came before the one we're interested in, the easiest way that I've found to do it is to just consider first all of the complete rows that come before you being, in this case, the thread we're interested in. So the threads that came before you, so we can do that by looking at our y value, our y index. So we have an index of 1 for the thread we're interested in over here. And that means that there's 1 entire row before us. Okay, that's great. So how big is an entire row? Well, that's what block dim.x is. So that's what the first 2 parts of our little equation down here in the bottom. We had 1 row above us, and it has 4 threads in that row. And then the last part is just the offset within the row, just like before. So we're the third thread in this row. So we add 3 to get to our position in the row that we're in. And we've already accounted for everything else before that, so we're done. And you can see here I use thread index.y is 1 times block dim.4 plus thread index.x is 3. So 1 times 4 plus 3 gives us 7, which is our ID here. I should also note that this is my way of looking at blocks and my way of identifying them and computing a rank for them. There's multiple ways to go about it. For example, you could look at it in a row major order, in which case the computation will be slightly different. But that's up to the needs of your computation. It's up to the problem layout. But you can kind of use this idea of counting threads and using kind of the dimensions you have, your column size, your row size, column index and row index as needed to figure out the unique rank of each one, no matter how your problem is laid out. If you're going to do something different, if you need a custom layout, I would recommend drawing it always, because that's really the only way you come to these conclusions about how to identify them and how to compute this, is by drawing it, at least in my opinion. So, okay. Next, we're going to go on to 2D with multiple blocks. But before we do that, do we have any questions about introductory 2D stuff?
I don't have a question. I just have something to say. For it, in my thesis, this is similar to where I used to identify in-video elements in a matrix. Like the way we're going and we say how many rows are in front of me, but it's 1, and how many columns are in that row. But it took me time to figure out, to comprehend. In my thesis, X is rows and Y is columns.
Hmm.
Yeah. But
Okay,
yeah,
so
this
that's
is good
actually
stuff.
good. So that's actually backwards of how I've done it here. But yeah, that's basically it, and that's something I'm glad you pointed out. Maybe without meaning to, but one reason we use this 2D layout for a 2D problem is because this very naturally can be used to navigate a matrix. So you can just plug in threadindex.x for the first value and threadindex.y for the second, and you get a natural kind of organization. Granted, you probably want to flip them if you're going to do that, but you can say value 0, 0, you use this thread, and then this thread can be value 0, 1, or whatever it is. And you can fork on matrices that way really easily.
I agree.
So, okay, well, good. Thank you for the commentary. I think that was good. But if we're ready to move on, I'll go on to using multiple blocks. Okay. So we're back here doing this thing again, and we made it more complicated, but not too much more complicated. So the process is relatively similar to when we didn't use multiple blocks. We're just going to use this dim3 type to create a thread configuration. So in this case, whoops. In this case, we want our blocks to have dimensions of 4 in the X direction and 2 in the Y direction. And then we want the grid, the thing that holds the blocks, to have dimensions of 2 blocks in the X direction and 1 in the Y direction. And we use that just the same way, and we can plug those numbers into the kernel configuration, just like we did before in all of the previous iterations. Just goes in the same spots, no issues. Then we get this mess of 16 blocks from that. So if you ever want to know how many threads you have, just multiply the numbers together. 4 by 2 is 8, 2 by 2 is 16, 16 by 1 is still 16. So 16 threads. And we've got this kind of arrangement going on. So you can see we have 4 by 2 in one block, 4 by 2 in the next block, and then we have 2 blocks marked by this red line, right? And then we only have 1 block in the Y dimension, so there are no more down here. So this kind of red line marks our block separation. So I just realized there's a typo here. This should be a 4. This block.x should be 4. But anyway, that's kind of what we're looking at. Now, once again, we want to index everything. How are we going to do that here? And you can see it is somewhat of a large equation here. You can ignore this little one. I'm not real sure where that came from. You can just ignore all of these. I think the image I had wasn't as clean as I thought it was. Anyway, so how do we go about this? In this example, I'm going to look at 15 because it's easiest to see this just by looking at the last thread, because then you kind of get to use all the values that you have. So we're going to go back to the whole idea of counting up or summing all of the threads before us. Okay, so how do we do that? Well, we're going to look first in the Y direction. What we would want to consider first is all of the completed blocks, or rather, I take that back, completed grid rows that we would have passed. Now, in this example, we don't have any because we're always going to be in block index 0. But you can imagine if we had a second block down here, so this block index was 1, we would want to count all of the threads in the X direction per block, all the threads in the Y direction per block, and then that times the number of blocks in a grid row. And so that's the value that we have here. So again, assume we have a 1 here. If we have another block, that means we have all 16 of these in front of whatever else it is we're looking at. And we get 16 by getting the number of blocks in the grid, which is 2, times the length of those blocks, which is 4, times, I guess, the height of those blocks, which is 2 again. And that's how we get this 16. That would be in every single row of the grid. I know it's going to be kind of difficult to keep those separate, but grid is the container for the blocks. Block is the container for the threads. So when we talk about grid dim, that's the number of blocks. When I talk about block dim, that's the number of threads in a block in a certain dimension. So that's this first value. In our case, it doesn't apply to the first one. Any questions on where that is or where it comes from? Okay. I will move on then. The second one is actually applicable to us. After we've looked at all of the blocks that come before us vertically, which means entire grid rows that came before us vertically, we want to look at any blocks to the left of us, in this layout to the left of us, that are fully done before us, right? So in that case, that does apply for us. And so we can look at the block index in the X direction. So for ID number 15 over there, which we don't know is 15 yet, that's what we're trying to figure out. Our block index in the X direction is 1. That means there's at least one whole other entire block of threads that is already been accounted for. So that's 2 in the Y direction and 4 in the X direction. That means 8 threads. So we've got at least 8 threads. That's what we've added here in this step, is 8 threads. Now I know you might be looking at this and saying, well, okay, so you got 8, but then you skipped all these and that doesn't make any sense. I get that. It's odd to see worked out on paper, but stick with me for a minute. We'll move on to the, oh, this should say Y. That's a bad thing to have wrong. This should be the Y direction of the thread index. So we've accounted for other blocks. Now we're focused solely on the block that we are in. The thread we care about is in. Now that we've done that, we can count for any rows above us that are completed. So if we have a Y index of 1, the thread index, then we know that entire row inside the block has been done. So that uses this block dim of 4, and we account for that entire row. So we add 4 to our total because we have a y index of 1, block dim of 4. So far, if you're following along, we've got 0 here, 8 for the second value, and 4 for the second value. So we're at 12. The last thing, just like with all the previous versions, is we have taken care of the blocks above us, the grid rows above us, the blocks to the left of us, the threads in the same block as us that are above us. Now we're just going to account for the threads that are beside us in the same row. And as always, that's just the thread index offset in the x direction. So that's 3 again. So 0, 8 plus 4 is 12. 12 plus 3 is 15. That's where we get this value. Does everybody have that? Because I'm going to be honest, if you all say yes, I'm kind of inclined not to believe you. Because I think that's confusing, and I've figured this out and put all the images together and everything. So please ask questions and tell me what we don't understand on this. Okay. Well, either y'all are all experts at this, or you're just too afraid to admit you don't understand it. But either way, that's okay. If you decide you do need help with it later on, there's in my guide online, there's a little bit more elaboration that may help, and also some more visual stuff. Do you have something that you wanted to add, Eva?
It's an observation. I don't know whether it's right, but we have extra dimensions here, right? Because the other time we had in each block, for example, if we had ID 15 for there was thread ID X and Y. We didn't have did we consider the block ID?
Before, so
1
before
and 0?
We did. So we didn't have the Y direction, but we did consider the X index here.
Okay.
So just to realign that one more time. In this example, the Y doesn't matter to us. What that's saying is an entire grid row, if we were to have that, if we were to have 2 blocks and we were down here somewhere, we would want to account for this entire row of blocks. That's the first line here.
Okay.
Then this X index for the block, we're in this block over here, right? This is block 1. This is block 0. We want to account for everything that's in block 0. Whoops. So that's what this does for us. Okay, we've got 1 block behind us. I keep clicking that on. 1 block behind us. And we want to account for all the threads in that block. And that's what blockdim.x and blockdim.y tell us. There's this many block threads in the x direction and this many threads in the y direction. And that's what makes up the entire block. So in this case, it'd be 2 times 4, that should be 4. And that gives us 8.
Makes sense.
Yeah, so you can imagine if we had a third block here, we would account for all of these. Block 0 and 1, that would be 16 threads. So the next thread of the next block would be, well, it would actually be 8, depending, it would change the layout, but anyway, you would add a total of 16 if you were in block 2 at that point.
Okay.
Okay. Does that answer everything?
Somehow.
Okay, well, if it doesn't, you can elaborate. I just, you were asking if we had any dimensions we didn't use, and we've used everything that we have access to at this point, except for the Z direction, right? We don't use anything .z because this is all in X and Y. There is no Z here.
I agree. Thank you.
All right. Good deal. Anyone else have any questions or misunderstandings, anything from what we've done so far? Okay. Well, the last bit I have here regards 3D simulation, 3D kernel configuration. So as it says, if you're lucky, you can avoid them because they can be a little bit tricky to kind of work with if you're trying to find a global rank value like we've been doing. That can be tricky for 3D configurations. However, if you have a tensor, which is like basically an n-dimensional matrix, if you have a 3D tensor and you have a value in each dimension, then this becomes kind of natural because you can just say, okay, give me the value at thread 0, 0, 0, 0, 0, 1, whatever it is, and you can use this layout to naturally access values and work with them. So in some cases, it still works out. This just shows how we can initialize these values and kind of do that layout. It's very similar to 2D. You just add an extra dimension. That becomes your Z dimension. The order of this will always be X, Y, Z. So you'll always need to put values in that order. And now each of the attributes we've been working with has a Z value added onto it. So you'll need to look at that as well when you're looking at like this idea of rank or any other computation where you're going to look at where things are located. And one way to think of these, the most natural way to think of these is as being in some sort of cube, which you can see here. I'm not going to ask you guys to think about how you would find an exact value in this mess, because it is quite frankly a mess. But you can see this is kind of a guide to help you think about what it would look like in 3 dimensions. The gray lines represent individual threads. So these gray cubes are threads. And then the red lines here represent blocks. Okay. So you can see we're 2 by 2 grid, 2 by 2 block sizes, and 2 by 2 by 2 by 2 is going to get you, should get you 64, even though it doesn't. Hang on, I need to think about it. 2 by 2 by 2 by 2 by 2 by 2. Yeah, 2 to the 6, so that is indeed 64. Okay. Okay. Over here, I've kind of sliced up the cube. So you can see from the back, this is our back slice. The next one, the third one, and this is the front face here. And I have also indexed all of these here. This is part of the article that this lesson is based off of, so it's also available there. I will also have the slides for you guys so you can look back at this. Again, not really going to get into any of this because it's unlikely you'll need to know it, but it's a reference in case you find yourself in that situation. So that's pretty much all I had. Are there any questions about 3D stuff or about the concept of kernel configuration, kernel launch, indexing in general?
About the 3D, is there an example where they use 3D? Because I've only seen 2D for matrices, but I don't know if I've seen any configuration where they use 3D. Do you have an example that you can mention that I can look up?
Are you asking for an example of like an application, why you would want to use 3D, or an example of how to, okay, the application?
Just an application.
Yeah, so really any sort of simulation will
Okay.
usually be 3D. So you can imagine like heat diffusion can be 3D. You want to map, a really popular one is fluid dynamics or aerodynamics, right? When you go to simulate how air is going to, fold over an airplane wing to measure its aerodynamic efficiency, that's going to be in 3 dimensions. A lot of things where you simulate real world forces and real world interactions are naturally in 3D because we live in a 3-dimensional world. And GPUs are a natural use for those kinds of applications because you can have each particle or each like quantum of space represented by a single GPU thread and have it calculate its value.
Okay.
Yeah, that's a good question. And if you are curious how you would go about getting these ID values, that is on the that is part of the article that I'm going to reference you guys to. If you're interested, of course, it's not a need to
Okay.
know thing.
Okay. Thank you.
Well, all right. If no one else has anything, then we will adjourn for today.